Hello, Western Australian Year 12 Mathematics Method students, and welcome to this afternoon's webinar, the third in a series of 5. This afternoon's webinar, Anti-Differentiation, with particular focus on trigonometric, logarithmic and exponential functions, and your presenter, Mr. Stephen Julian. Now, at this point, the dulcet tones of my voice are hopefully streaming beautifully through the audio of your computer. However, if you do encounter audio difficulties, can I advise you to phone in on your telephone on the toll-free number 1800 708 203 and enter the event number 85673-356. I will also type that information into the chat window for you. Also, during the session, can I please encourage you to make use of the Q&A panel, and when you type in your questions, can you direct them to all panellists, please? You click on the tab, pull-down tab, to all panellists. There are a few of us watching, waiting to assist to answer your questions. Also, can I please thank you to those of you who have given us feedback following the first 2 sessions, and it's all very encouraging. It seems that the pages, the tips and the menu navigation from Hayley, and then the further calculus from Stephen has been quite useful. So great to hear that. And tonight, Mr. Julian will have you working a bit harder once again, as he takes you into the anti-differentiation applications. So without further ado, I shall hand over to the jewel of the Julians, the man from Mandurah himself, Mr. Stephen Julian. Stephen, how are you going, mate?
Good evening, Brian. Can you hear me?
I can indeed.
Okay.
The ball is in your court.
Okay, thank you, Brian. Okay, I'll just wait for my computer screen. I know it's not quite come up yet, so I'll just give people a chance. Yep, now it should be coming up. So, yeah, good evening, everyone, and hopefully that's come up okay, Brian. That's all good?
Looks okay on my machine, mate.
Fantastic. So I hope everyone else has got the same view looking up on the screen. Now, I've just been playing around, just doing some final last changes to my PowerPoint, so I better quickly go back to the start. So, yeah, hopefully everyone's enjoying much nicer weather over here in WA. I know it hasn't been great lately, so hopefully everyone's enjoying some actual nice sunshine for a change. Tonight, as Brian mentioned, we're actually going to look at anti-differentiation, trig functions, logarithmic and exponential functions, and obviously show you a few tricks and hopefully follow on from a few things from last week. The first thing, however, I want to do tonight is, tonight we want to be a little bit more interactive with you guys. We want to actually see you have a go at a couple of questions and particularly give us some feedback. And I know Brian will be very eagerly watching what comes through, along with our panel of normal teachers who are sitting in the background actually watching what's going on. So, to start with tonight, we're going to have a little bit of a quick quiz. I know my students at school love the good old quick quizzes, just to see whether they've remembered what they've done from previous lessons and particularly from previous concepts that we may have done on other lessons. So tonight what we're going to look at is just quickly review, and this will be a very quick review, of a couple of the key presses that we had last week. So what I would like you to do is I'm going to get you to have a go at these. Hopefully you've got your handhelds with you at home. And I'm going to get you to have a go at each of these questions. Now, I will say be careful with questions 2 and 3. I know we talked about the function minimum idea last week. Just be a bit mindful what might be happening with functions such as x cubed plus 3x squared, take x, take 3. So we might have to come up with a slightly different way. And question 4, again, it looks at a couple of the key pushes that we had previous last week. Now, the way I would like you to do this, if you are sitting there at home and eagerly watching, is I want you to record your results through the chat or the Q&A. Now, the way we're going to do that is I know that some of the button pushes won't come through just quite as well on your on the chat as what it does on the calculator. So if you're going to do a divide, and I'll just put this at the side of the screen, I'm actually just showing you that if you do a divide, if you can just do it as a the division diagonal line, and if you're going to put in something like 16, take t to the power of 2, to show the power of 2 on your computer, you should have the little up hat that looks like that. Now on this one it makes it a power straight away, but we'll understand in your answers if you mean power that if you have the up hat 2, you mean to the power of 2. So I'm going to give you a couple of minutes. I just want you to have a go. I know some of you have probably started these questions already, just to see whether you can come up with some answers. Now, in between each, if you can just put the number, so 1, 2, 3, 4, and I'm going to give you about 2 or 3 minutes to just see whether you can work through those problems. And while you're doing that, I'm just going to jump over the chat. I know you won't be able to see me doing that. And I'll just see whether we've got some people who are answering the questions as they go. So hopefully people can have a go at that. Brian, that's going well at your end as well?
All looks pretty good. I reckon
all looking pretty good?
Too.
I hope you can, Brian. That would be really good. And as I said, hopefully the students are having a go while I'm babbling on in the background.
We're working them hard.
Working them hard. Good to hear. Okay, so I won't give you too much time. I'll just, again, just see if we get 1 or 2 people coming through with responses. Okay, we've got an MG who's already come through. MG has given me a couple of responses. Looking pretty good, actually. Looking very similar to ones I've already worked out previously. And that's come through privately. Now, what I will suggest to any of the participants, if you are sending your answers through, if you could actually do it to possibly to all panelists, so not just to me privately. If you do, then the other panelists who are watching for your answers can also see. So again, I'd suggest that if you can send it through to all panelists rather than just to me privately. That way, while I'm talking with the other work, you'll get a chance to actually check things and have them check for you as well. If it comes through to me privately, I'm the only one who can see it. So yeah, Brian, any responses coming through to you?
No, they're just writing to you privately by the looks.
Yeah. I must be, well, I do recognise this MG person. He's pleasingly one of mine. So yeah, as I said, hopefully we'll get a few more responses coming through.
I would have thought PF might know the answer to this one.
Yeah, I think there's a few other names on that list that I think I recognise who probably should know, so I'd hope to see a couple more responses come through. Actually, I think there's a BT who maybe knows a few things there as well.
Mm.
Okay, I'll just give people who are wanting to respond maybe 1 or 2 more minutes. Once you've done question 1, if you want to have a go at question 2. Oh, yes, an HO has just come through with a number that looks pretty good for the find F-1. Okay, we might leave it there, Brian. What do you reckon? We might move on. Just see. I know that we've got probably a couple of people who are a little bit reluctant and shy to have their names popping up. So what we'll quickly do is just maybe talk about particularly the maximum and minimum problems as well. But I'll just if I delete that. So just quickly going through our key presses from last week, if you are wanting the shortcut for differentiation, shift and minus will bring that up nice and quickly for you. If you're doing T, you don't have to have it always as X. Control and divide will bring up your fraction template. Then we've got 1 over 16 take T squared. And if we do that, we should get our derivative. Now, just another little quick one for you. I know last week we talked about the idea of calculus and you've got derivative of the point. Now, in this case, our variable is t rather than x. Our point is 1. If we go OK. Now, rather than having to retype that in, we could have defined it, or what we can do is go up to the top, just move your cursor to the side so it's just inside the bracket, then shift and to the left will actually highlight that. Control C, we can copy. And then if we move down to our spot inside the brackets for the next question, Control V, and we've got our answer. And I did notice there was a lot of 2 over 225s and 0.08s. I think I saw a few answers like that coming through. So a few answers look pretty good. And if we wanted to check that as a decimal, I think most people know by now, Control Enter. Oh, actually, sorry, it was 0.008, etc. So look like the answers that came through to me look pretty good. So that's the first one. Now, the next one I just want to quickly touch on is the menu. So if we, again, look at menu, calculus, function minimum. Now, there is a little bit of a problem with this one. If we type in x cubed plus 3x squared, take x, take 3, what it's going to do if we put the comma x at the end is it's going to give us x is equal to negative infinity. So obviously it's looking at the idea that what is the smallest value that the function can have for an x value, and it's going to happen at negative infinity. And if we know what that graph looks like, we can probably visualise that that's showing that the tail's going right down. So we're probably better off coming up with a better idea for this one, and that may be from a graph point of view. So if we go Control I, and if we draw it graphically, and again, we could have probably defined this as a function. That would have been a nice quick way rather than having to re-enter it each time, and we talked about defining last week. 3x squared, take x, take 3. Because we're actually now, and you'll notice that our graph is obviously dropping off, so we could have maybe restricted the domains as well. There's a couple of things we could have done to look at this a little bit more localised. But if I now have a look at this graph and say, okay, I want to work out what our local minimum point is, so this one where my hand is hovering, I could go Menu, Analyse Graph number 6, number 2 for minimum. Just move your cursor so we're at our lower bound, so just somewhere between our maximum and minimum. Press Enter or the mouse button, and then if we go to the right, and hopefully people may have been able to play around with that and found out that the minimum point is happening at 0.155, negative 3.08. The next one we could have, looks pretty good, doesn't it, Brian?
Yeah, it is good. It's brilliant, yeah.
Yeah, really good. And I'm going to show a couple of tricks shortly on how we can do that with integrals with the graph as well, which will hopefully make things a little bit quicker and shorter for people to deal with. Okay, just very quickly we'll touch on the maximum as well. So 6, 3, go for your lower boundary, go for your upper boundary, and we can grab that point and just move it into somewhere that's a little bit more easier to read, and there's our maximum point for anyone who was after it. And again, we are talking about a localised maximum. Obviously, the reason why the calculator was giving us negative infinity and infinity is we hadn't restricted the area that we wanted to look at within the graph. The last one, just touching on our review, is the tangent. So I'll go back, Control, and back. Now, we want to do a tangent, so I'll come up to Menu, Calculus, Tangent, so number 9. Now, hopefully people, it may have worked out that we can actually now use f1 of x. Now, the reason why we can do that to actually represent that function is I've just drawn the graph of that function on the graph page, and the labelling for that was f1 of x. So now it's actually going to remember that that's the defined function for that particular situation. We can then remember, if you remember the syntax last week, we can put x equals 1 with a comma, and we end up with our tangent line. So again, now that we've got it defined even just as a graph, we didn't have to define it on the calculator page, we can now use that as our ongoing function for that particular problem. Now remember, if you are doing this in an exam, y equals at the start of that, because it's a tangent line, so it should be y equals 8x take 8, not just 8x take 8. So that's just a couple of quick review questions from last week. Hopefully people did well on those. I might skip over for the next few slides. I was going to touch on a few things we didn't quite get to last week, but I think we'll go to the advertised part, and then if we have time at the end, I might jump back to a couple of those other little minor tricks that I was going to show you. So now to this week, our focus is the review of Calculus Menu Options Part 2. There's really only two major ones that I would suggest as regular things that I would use with my classes. There are obviously other tricks within algebra and under the calculus tab as well, but we probably mainly need to focus on here tonight the menu in terms of what we can do with integrals and sums. So having a look at the menu options, if I go into menu, and I might keep on using 1.1, we're going to look at the integral sign this time, so calculus number 4, and we're going to work out number 3. So number 3 will actually give us the idea of the integral, and we can do definite or indefinite integrals. If we have x squared and say dx, and this is a pretty easy, straightforward one. We'll look at a more complex one in a moment. Straight away, hopefully people recognise that that's x cubed on 3, increase the power by 1, divide by the new power. But there's one thing that we are missing there, and I'm not sure if any of the participants have picked up straight away through the chat. What do we need to include if we're going to use the integral in that sense, so the indefinite integral? So if anyone on the out there in the student world or teacher world would like to just say, what should we include with that answer?
I know.
You know, you're jumping up and down?
Yep.
Yep, very good.
Oh, yep.
Yep, so yes, actually, MG has just come through with an answer, and it's the plus C. And again, I'm very happy to see that MG is making that comment for various reasons, and I think he'll know. But yeah, well done, MG. Was that what you were going to say, Brian?
That is exactly what I was going to say. The HO crew, there's a team of them there. They've got a brains trust there, apparently. And,
okay.
they are right on the money as well.
Oh, good to hear. Very pleasing to see. Obviously, a couple of schools have decided to do this as a bit of a group effort, so that's great to see as well. So thank you for that, HO, and thank you for that, Brian. Okay, the next one I just wanted to touch on is the summation sum, and then I'll jump to my next slide, and we'll go into a little bit more detail with the integral sum, the sign, sorry. So menu, and we're going to go into calculus and sum. Now, this sum symbol, particularly for things with probability, which we'll be touching on next week, can also be very, very useful. This one here, I might just make it again a fairly straightforward one. If we're talking about the numbers, they're going to range from the first term being 1 through to maybe 10. And let's say we want n times by x. And because we are doing 2 variables here, it is a good idea to put the multiplication in. Otherwise, the calculator will assume that you're actually talking about nx rather than n times x. Now, in this sense, what we're actually creating here is we're looking at n being 1, so it'll be 1x plus 2x plus 3x plus 4x all the way up to 10x. And if we press enter, straight away the calculator can work out 55x. Now, that can be useful for some of your you're getting into your integrals and you're looking at summations of rectangles. Again, particularly in your probability work, some of the stuff with expected values and getting into variance. If you haven't seen that symbol before on your calculator, it can really speed things up for you. And there are a couple of other shortcuts, particularly for probability, that we'll look at for next week. It's just a little bit of a plug for next week's session. Okay, moving on. Question 8. Now, again, I'm going to give people a quick chance to have a go at question 8, so both finding the derivative of ft and then seeing if they can work out the connection straight away. Should be a fairly clear connection. So just give people a chance just to enter that one into their calculators and then see if they can come up with some kind of connection. And again, I encourage people to just send through, particularly if Brian can keep an eye on those questions and answers, just what connection might be happening between RA and the first part of part B, which is our hence part. Can we see some kind of connection? And again, I do encourage you to try to use your calculator here rather than using manual options. This has come from a trial paper where the expected idea is to work with a calculator. So again, I'll just give people a chance to see if they can see a connection straight away, and if they can send through any ideas that might be linking particularly the first part A with what is happening in the indefinite integral in the first part.
And of course, a reminder that your calculator setting will have to be in radians.
Yeah, good point. Thank you for that, Brian. Yes, very good point. You will notice at the top of my screen that I have got it in radians. But yeah, please make sure any of the calculus steps that you're doing with sine, cos, or tan, particularly sine and cos are the main parts of the Western Australian Methods course. You are expected to be able to do tan more as a quotient rule question using the idea of sine and cos. But, yeah, anything that you're involving calculus with sine, cos, or tan, make sure you're in radians. Okay, not getting too much coming through here, so I think people may be still playing around with that. So let's see whether we can find the connection. So, again, we're looking at f dash of t. Oh, here we go. An interesting answer from MG. Okay, let's see. It looks pretty good, actually, and not bad use of the pi rather than writing pi. What connection appears to be happening there? Well, we should know there's something happening between the derivative and the integral. And, another answer coming through from MG. MG's very active tonight, Brian. I don't know if you're seeing all his answers flying through.
Yeah, he's decimalised the previous result,
yep.
which I generally prefer the exact answer. Particularly as it is in there. But he can do both, which is fine.
Yep, that's right. Okay, let's quickly check if these answers are coming through from some of our participants working. So we're going to start with the idea of differentiating the ft function. So let's go into derivative. We're going to keep it in terms of t. Some students like to just use x all the time and then remember to convert it. It can be a little bit dangerous in the exam to just make sure that you remember to return it. So I'm going to do the square root of sine, then we're going to do pi, and then x, and let's see, t. Now I've gone and done what I just warned people not to do. Shows it can be very easily done. Now what we should notice is that answer looks fairly familiar with this integral sign up on the next part. So we would hope that if we integrate that particular expression, we should hopefully end back at what we just had a moment ago. So the shortcut for the integral, shift plus. Now what I'm going to do is rather than type all that in, I'm going to move up and copy it. So Control C. You can actually just press enter, but you've got to be careful it goes into the spot you want it to. Control V. And then we're going to put T on the end, press enter, and lo and behold, we're back to the original answer. So sometimes in the exams, they will ask you to sort of make a comment about what do you notice. And in this case, that confirms that we've got a bit of a reverse situation going on, that we've got reverse operations between the derivative and the integral section. Okay, just quickly looking at the idea now of doing the definite integral. Whoops, that was a silly thing to just do. Let's just do that again. So we'll go Menu, Calculus, Integral, and then I'm going to look at now, we can put fractions. This is actually a handy little feature. We can put fractions into our limits. So Control and divide like normal, 1 over 6, move up, Control, divide, and 1 over 2. Now again, I've just copied before the previous function part, so let's go Control V. Ooh, and again, I picked the whole thing. That was clever, so let's go back up. I'm having fun with our good old copy and paste here, Brian. Control C, and let's go back down here.
The fractions there for the endpoints, and I particularly encourage students to do that. If you put decimals in, for example, 0.5 instead of a half, it runs the risk of decimalising the final result rather than showing the exact answer.
And especially things like 1 over 6, if you haven't got an exact decimal, so either recurring decimal or non-terminating decimal, it can sometimes lead to a little bit of accuracy problems as well. So let's see how the calculator handles this one. And you'll find that we've got a pretty interesting result there. I know that on the paper that I originally got this from, it did actually allow you to have the decimal answer. So again, if we go Control and Enter, and we've got our decimalised version of that, and pretty good exactness there as well. So that's just showing you some of the integral signs. Now, I'm just going to move on now. Sorry, Brian, what were you going to say?
I was just going to say it confirms what was submitted.
Yep.
And I think the important message there is read the question. If the question says exact answer, then you needed to put the third. But if it said, for example, 2 to 3 decimal places, then you must decimalize and round appropriately. For example, if that said to 3 decimal places, you would have to say 0.293.
Yep. Yeah, exactly, Brian. And I'd be strongly recommending, which is what I do for my own students, is highlight information like that within the question when you're doing it on the exam. So either underline key things like how many decimal places, whether it says exact. I have a feeling, being a methods course, I think we're going to have a lot of questions on the end of year exam that are going to talk about exact answers. So please try to at least have written down somewhere within your solution. If you are going to show the decimal answer, at least make sure you write down the exact answer first. It's always a safe thing to do. That way, if the markers are marking your work and they go, oh, well, we can see you know what the exact answer is, and plus they've written down the decimal, they'll at least, they should give you still full credit, even though you've gone further than what you need to. if you just write down the decimal without the exact answer, then you're running the risk that you'll get nothing for the final solution. So just be mindful of that. If in doubt, make sure you've got the exact answer written down before you do the decimal. Okay, moving on.
I tend to think the default setting is give an exact answer unless you're told otherwise.
Exactly right, yeah. So always aim for that. And again, as Brian said, probably the main story is make sure you read the question. And again, underline things. If you think you're one of those people who will make mistakes like that in the exam, underline key things when you read it, and then make sure you follow that when you finalise the question. Okay, let's move on to question 9, which is getting into some of the graphing stuff. And this one particularly is a really, really nice question that can show you a lot of the features that we can do on the calculator in terms of working through problems. Now, I'm actually going to start a new document here just so I don't run the risk of having things starting to double up in terms of variables that I might be using. So last week we mentioned to get a new problem, up to doc, into insert, and go into problem. Okay, and I'm going to start by, it says start with sketching the graph, so I'm going to sketch the graph. So number 1, we've got x times x take 1. Now I'm hoping that people straight away can sort of visualise this as a graph. It's going to be a cubic. Okay, so let's draw that. And we should get a nice looking picture like that. Okay, now the next part of the question, again, I'm going to give you a minute or two just to have a think about different ways you could actually do this, and then we'll talk about some shortcuts and some tricks just in case that you don't have a particular method for doing it. Part B says find the area enclosed by the graph of f of x equals, so the function, excuse me, and the x-axis and the lines x equals -1 and x equals 2. So I'll give you a minute to either go into a calculator page, or if you're already aware of some of the tricks you can do on the graphs, I'll give you about a minute to see if you can come up with an answer. And again, if you can just shoot that through and we'll see whether you're on the ball. And again, we'll try to aim for maybe a decimal answer this time. So we'll go for something around about 2 decimal places with our answer, just to change things up. So again, what we're after is the area enclosed by the graph, the x-axis and the lines x equals -1 and x equals 2. And we'll take that answer to to 2 decimal places. And if you get an answer, shoot them through. Okay, you've got, oh no, that was from the previous one from MG. Haven't seen anything through yet. Oh, got a couple of answers coming through. Okay, MG, again, very active tonight. Good to see. Given us individual numbers that he's adding together, now it'll be interesting to see what he comes up with for the whole thing. Now, we've got a suggestion from HO that it may be the integral of the absolute value of the graph. That would be good as well. So there's another method that we could possibly come up with. So again, maybe we'll start just having a look at a few of these ideas. I thought I'd just leave a bit of silence there for a couple of minutes in case anyone was trying to log in, just to totally confuse them to think that there was a picture but no sound. So just to keep them on their toes. Okay, let's have a look at a few ways that we can actually do this. So the first one I'm going to look at is just looking at the graph, and there is a way that we can do this without having to worry about absolute value signs or anything else. I'm going to go into menu, number 6 for analyze graph, and you'll notice that number 8 is bound area. So I'm going to go into bound area, and it will say to you down the bottom, we want to know which graph that we're actually going to pick. So obviously we're looking at the only graph we've got that's visual, but it will then come up with what's the second graph. Now the second graph is obviously the x-axis. Now you notice that when I hover over the x-axis, it actually gives that as an option. So let's click on that. Now we'll say lower bound. Now if you try to do this manually, it can get a little bit tricky. So what I'm going to suggest we do here is our lower bound is actually -1. So I'm going to use the negative button. Now, I know on my screen it's coming up with the minus sign. It's a little bit hard on the computer that I'm using, but you're probably better off using the negative sign under the 3. But I'm going to put -1 using our minus sign. Now, you'll notice that straight away it's starting to show area, but it's showing it to the wrong direction. And part of the reason for that is my hand is actually lower than the minimum value that I just put in. So I'm just going to move this lower bound and move it to the right of the value that we're currently trying to find. Now, our upper bound is 2. And notice again, I'm just typing the number 2, and it's automatically coming up in like a square box next to the upper boundary. If we press enter, what you'll find is it's actually giving us the correct area, not the actual integral for that, but it's actually the correct area for that particular graph. So it's actually giving us the 4.58 that one or two of you actually sent through as a solution. So that's actually not a bad little feature. We could actually now insert a calculator page, so Control-I. Now, because we're talking about area, we might want to now look at Part D. So I'm just going to jump straight to Part D. And again, this is just a couple of different ways we can do it. I'm going to do Menu, Calculus, Integral. We're going to go from our -1 to 2. Now, as HO sent through, we could actually use the idea of absolute values. So if I type in ABS, open bracket. Now, here's another quick little trick. Because, again, what we talked about before with the previous graphing, I can actually put F1 of X because we've actually now graphed that function. So it actually will now recognise that as being the function that we've already used as our graph. And if I press X into our DX part and enter, ooh, what have I got happen there? I think maybe I might be an exact value sign. Let me just check that for a minute. I've done something that has made this not like me. Let me just go to Settings, Doc. I'll just go to Approximate, see if that gives us a better answer. Otherwise, I've just typed in something incorrectly there. That's better. Okay, there's a good little quick message if you get something strange and you're after an approximate answer, or even if you get something like that, always a good idea to either go Control-Enter, see if it comes up with a decimal answer, or just go back into your settings and change it into approximate. I'm just going to go back into that because I know that will cause a few problems for me later, so I'll keep using the Control.
Yeah.
Say again, sorry, Brian?
I think it was okay the first time. It just looked a little bit unusual.
Yeah, it just came out as an exact answer, but it hadn't actually worked out the full thing. So Control-Enter would have solved that little problem for me. But again, you'll notice that by using the absolute value signs, we actually get the 4.58 come up, which is exactly what we wanted. Now, we could go back to the graph, have a quick look at that one again. So I'm actually going to do this a little bit differently now. I'm going to move into 2.3, so Control-I. Let's look at it from a graph point of view. So again, we're going to find the graph of the absolute value of F1 of X. We're going to graph that. And what we should notice now is any of our negative areas, anything that was below the x-axis, has now moved above the x-axis. So that means we can not only look at it from a bound area point of view now, we can actually also look at it from an analyse graph integral point of view. So if I go analyse graph and integral, I'll go to my lower bound of -1, press enter. Make sure you're to the right of the value you want, push 2, press enter, and again you'll find that we get that area. Oh, geez, I've just moved that. That was clever. Let's just go Control-Z. Always good when you move things you don't want to. Control-Z again, and you'll notice there that I actually have my bit of text, if I can just get on that properly, of 4.58, doing it in a slightly different way. Okay, I'm going to just skip over a couple of things here because, again, I'm aware we've got a lot of really good stuff to do. A lot of these slides are available for you now, or actually all these slides are available for you on the Google Share Drive, which I'm pretty sure have now been uploaded. I think just to give myself a couple of minutes break and to let Brian have a go at something he wanted to look at, I think we might just jump over to the fundamental theorem of calculus here, Brian, and give you a couple of minutes to go through that, if that's okay.
Right, mate. I was just answering one of the questions there. Was in 3 parts. You might see it when it comes through. There was an error in the first part, which I was just going to, it should be 13 on 12 rather than 37 on 12. I'll let you play with that.
I'll have a look at that in a minute. Thank you, Brian.
I shall grab the ball to me, which is probably just a transcription error, which isn't a problem, and well, it's not a major problem, shall we put it that way.
Okay,
and again, the argument for always showing your working. So that if there is a transcription error, you can fix that up.
And that gets back to also the idea I mentioned last week. If you are going to use the notes page idea, not to just rely on it giving you answers straight away, but making sure that you try to get it to generate at least some of the steps as well, so you can use it, if you're going to use it for that reason, that you actually can see the working out as well. So, okay, over to you, Brian.
Righto. Okay, so fundamental theorem of calculus is these weird-looking things here where our endpoints, we've just been doing some definite integrals, but where the endpoints themselves are looking algebraic. And what's happening here, I'm differentiating an integral, but that's kind of looking weird, isn't it? I'm differentiating with respect to x, but the variable within the integral is t. It's actually not too difficult on your calculator. And I'm going to graph it as well. I'll just get my calculator up on the page, which is sitting over here. And I'll start a new one, because I've been messing with this before. So I can type the whole thing in, and we'll be okay. But what I want to also show you is what it looks like graphically. So to get the differential, so remember that shortcut, shift minus, and that was actually happening on those slides at the start of the webinar as you were tuning in. So, and within the differential here, I'll put the integral, and I can make it definite, and I'm okay. This is a CAS-based calculator. It can handle algebra. That's its job in life, basically. And here's our fraction here. Shortcut for the fraction is Control and the division key, and I've got 1 on x. Now, you know the integral of 1 on x is log x, but what's happening when I do this, sorry, that should be 1 on t. Make sure we get our variables correct, dt. So what's happening inside the bracket, so this will work out the whole thing, and it'll give us the result there. And what I'll do, first of all, is I'm just going to so there's our 1 on x. We've answered the first part of the question there. But let's just take a look at that integral again. If I had the integral, let's start with, 5 there, and shall we say a 7 there. So it's a definite integral of 1 on x. So let's go with this again. I didn't do that. Go there. Control, that's the one. 1 on x dx, or 1 on t dt. I'll run with t. That's the variable we're using there. So what's going to happen? That's the log of 7 minus 5. Okay. If it was an indefinite integral, it would just simply be the log. So let's just have a quick look at this. So it would be the log of t. But because it's the log, when I do the definite integral with endpoints from 5 to 7, it will be the log of 7 minus the log of 5. So what I've got there, I'll just show you, log of 7, and remember your log rules here, minus log of 5, which is log of 7 minus 5. So log A minus log B equals log A divided by B. So that's what's going on there. So that's coming back to what our question was, this bit here. So it says, hence, show that if we had the integral from 1 to 2 of the antiderivative, of that thing, we're going to get log 2. So that's basically saying I'm going to take the integral from 1 to 2 of this. So let's come back down to this line. So the integral from 1 to 2 of, uppercase f x. Now I could copy all that up there, or I could just simply put, 1 on, so we know that it's going to be this here. I could just put 1 on x. So I can copy all that in, or I can just put 1 on x. So let's just have a run with that. dx, and it's our log 2. But for a show question, I would probably expand that out. I would say that it's log 2 minus log 1, same as what I've just done here. And if I've got log 2 minus log 1, that would then be, just as log 7 minus log 5 is log 7 over 5, log 2 minus log 1 will be log 2 divided by 1, which is 2 divided by 1 is 2. So we've shown what we were asked to show. But what I wanted to illustrate graphically, and I'm just going to change it a little bit here, back in our PowerPoint, because when I graph it on the calculator, it has to graph in terms of x. So I'm going to graph 1 on x, and then let's take a look at the area under that from 1 up to a point A. So let's just have a quick look back at our calculator, and I'll put in a graphing page. 1 over x, that's what it looks like. Okay, and let's find the area under that, because remember we were looking at integrating from 1 up to well, if I could integrate from 1 to 2. Let's just get I'm just going to zoom in. No, that'll be fine. Just like Stephen just showed you, analyse the graph. I could get the bounded area, this graph and this, and the lower point could be 1, or let's just type it in as 1, and the upper point being 2, and there it is. So it's saying that the area under there is 0.693. It does a decimal, and by the way, this, if I take the log of 2, that's what it is, 0.693. So that's why that's the same. But what's actually happening with that indefinite integral, and again I'll come back to this PowerPoint, what's happening with the indefinite integral is it's not going initially from 1 to 2, it does here, but it's going from 1 to A. So let's have a look at that. So I'm going to put a point here, and let's just make it. I'm looking at time. I'm going to switch across to the one I built before. What I did here, I went from 1 up to, instead of 2, I made it A. And I can move my A point. I've got it on a slider here. So here's the area when A equals 2, but let's say A was more. So that's what's happening in this situation, is we're integrating from 1, from x equals 1, and we're going up to a value that we're just calling A. And so depending on what A is, we will get a different integral or a different area under the curve there. The two parts of this fundamental theorem of calculus, as it's referred to, I've generally thought of it as being adding in sliders. I'd love to show the sliders, but I'm conscious of time. I might try to add that in. I might try to illustrate that maybe a little later as we go. So with the fundamental theorem of calculus, so this is the first bit here. So we've got the derivative of the integral will come back to the function itself, where x is the end point. So I'm going from A up to some end point x. And the second part, I generally think of it as being, that plus c. I tend to think when you've got endpoints in, the plus c effectively becomes negative the antiderivative function with a inserted. And I did have a couple of others that you might like to try. We're going to run out of time though, but the same deal will work. And you can do this manually. Remember, as wonderful as your calculators are, the first part of your exam is non-calculator. Use your calculators to help you develop your understanding of what's going on. So I've got a function, it's t cubed, and I'm going to integrate that from 0 up to a variable point x. But you should be able to do this manually the antiderivative of t cubed is going to be, what have we got? T to the 4 on 4, and then you would write that out, first of all, substituting in your x, and then subtract the same thing, substituting in the 0. And same sort of approach here. The message is don't freak out just because you've got algebra in the endpoints. I'll try to answer that question about the slider, but I'll hand back to you first, Stephen.
Okay, thank you, Brian. Oh, excuse me, I'll try that again. Thank you, Brian. Okay. Voice is just broken at my age, that's all right. Okay, just waiting for the slider to come over to me. Yeah, I also saw that question about sliders, Brian, and
yep.
That one I can probably deal with at a school level because it's actually one of my students. But if you can send something through, that would be great.
Sliders
but if you can't, I'm quite happy to try to deal with that one. So that's fine. Okay, I know that we're getting towards our last 10. Oh, sorry, Brian. Was that you? No.
That's good.
Okay. Let's go. Sorry, mate. You can see me. Good. Okay. We might just jump towards because we've got 10 minutes to go. Just having a look at maybe a little thing that I've put together. I'm just trying to find the question that I would like to look at using this. Okay. Just coming back to the area under a curve one, and the main first few parts of this are very similar to what we've done in the previous questions. So again, looking for area, putting in all your inputs. But I guess the part that I want to have a look at is part D. Use a calculus method to determine the increase in the area as A increases from 3 to 3.1. Now the question in full is about a graph that has y equals e to the x between x equals a and x equals x equals 0 and x equals a, and it is asking you to find the area in terms of a. Then it talks about finding the area if little a is equal to 2. Goes on and says find the value of a. So we might actually do that one because that is a little bit different to some of the things we've been doing in the earlier parts. So again, I'm going to open up a new problem just to start afresh. I'm going to go into Add Calculator, and I probably just want to focus on this Part C and Part D part. So find the value of A if the area is 32.1 units. So we're actually trying to solve and find what the area would be. So in this case, using the solve function, 3 and solve. Because we're trying to talk about area between a curve, we can go into menu, and we're going to look at calculus, our integral. We know the lower limit is 0. We know our upper limit is a. The function that we're actually trying to solve for is going to be e to the power of. Now, this was something I was going to talk about earlier. Remember that we can't use just the letter e because it will treat it as just being some kind of value, some constant, so we'll have problems. We've got to use the e to the x button, or we can use, there's an e option under the pi button. So we're going to have e to the power of x, take 1. It's going to be x that we're differentiating with. And then, not take 1. Again, just read the question. Would be good if I went through the whole problem. So e to the x dx, what we actually want is for the area to be equal to. Now notice when I actually didn't go outside the integral sign and I put equals, it suddenly tried to put the x in brackets. So it's another little thing just to be careful of. We actually need to push to the right once and then push equals. We want 32.1 as our area, and then we're going to solve for. Now, in this case, we're going to have a being substituted in. So a is actually the thing we're going to be solving for. If we press enter, you'll actually find that a value of approximately 3.5-ish will actually give us the area that we're after. And we can confirm that. We could actually go back in and do either a graph or just use the integral directly. So integral, 0, let's make it roughly 3.5. Actually, no, yeah, we will. 3.4995. We'll take it to 4 decimal places. I could copy that value down. E to the x dx, and let's see that it's roughly the 32.1 that we want. And you'll notice with a little bit of rounding error there, we could. Again, you could have actually gone up above and copied down the a value by highlighting. And the way we would have done that is if I just go up, push to the right, and then shift, and then you could just push across and highlight that value. That would give you an exact value coming down if you're in approximate or if that's the answer it's giving. The one I wanted to have a look at was Part D, use the calculus method. Now, I've actually prepared something that is available again on the share drive. It's actually a incremental formula notes page, and we talked about these last week. Now, this one you, again, can easily upload and then put on your own calculator. But with this incremental formula, you'll notice I've got one in here already that I've just taken from one of the local papers, which is 3x to the power of 3 plus 2x take 1. What this will do is, using the incremental formula, we need to know what the dy dx is, so I've worked out the derivative of the function that's being defined. It'll then give you the derivative. We can then put our initial value of x, our new value of x. It will give us the change in x. And then using the incremental formula, it will tell us what the small change in y is, if y is the variable that we're working with, and then it will also give us the new value. So coming up to this one here, we have the graph. So if I go into our box, and again, this is all available for you on the Google Share Drive, I'm going to put in e to the power of x as our function. So that's done. You'll notice now that it's already differentiated for us. However, the one thing we do need to change is our original value was 3. So enter. Always when you go into these maths boxes and change things, always remember to press enter at the end, just to ensure that we have the change being made. Our new value will be 3.1, so press enter. You'll also notice that my outputs aren't coming up with any of these boxes. One of the options you can do when you're doing your own notes page is Control and Menu, and under the Math box attributes, number 8, you actually have a box here that says about input, output, and whether you want to hide it, show it, and have whatever detail that you actually want to include. So I'll just cancel that because I've already hidden it. So let's just go back outside our box. Now what you'll notice here is down lower, it's now changed my x, so the change in x is 0.1. Using the incremental formula, we now have a small change in our y, and it's now telling us what our new value of y will be. So just by changing things up the top, and so the two things if you're going to use this notes page is remember to change your formula and change the values, your initial value of x and your new value of x, and that will give you all the other details. And again, it gives you a nice little bit of structure as well. Okay, I'm noticing the time. I was going to try to go through one more problem with you, but I think rather than trying to rush it, which is never a good idea, I will just draw your attention to the PowerPoint, again, that's available on the Google Drive. One about rectilinear motion. Some nice little ideas there. We might actually use that as our remembering question or our quick quiz question for next week, just to get people thinking about integration before we move on to probability. But again, a couple of very nice little features in there that we might touch on just from a graphical and calculator point of view from next week. So rather than rushing through that, Brian, I think we've covered a fair bit tonight. So how are you feeling at your end, Brian? Any other questions coming through?
Yep. Yeah, mate. I was just starting to type in a response to the one we did way back earlier with the 3 parts under the cubic. Now, the 3 fractions are the first, because I've got people doing it bit by bit. The 3 fractions would be 13 over 12 is the section from -1 to 0. The second part is 5 over 12. That's the 0 through to 1, and of course that's the bit below the x-axis. And the third part, 37 over 12. That's the last bit. Yeah. So so I started to address that before, but I didn't get it all typed in. So it's actually the last fraction there that was different.
Okay. And I was going to say, Brian, just another one that came through just while I quickly look back through the chats as well, from PF, just one of the things that would have solved a little bit of our issue from earlier with getting an answer that was very algebraic and we could get an approximate. That was I think the answer was 4.58. Having it in auto mode will make that a little bit easier for us, so we'll generally find that the calculator can work out what's appropriate and what's not. So again, just get familiar with your different modes, auto, exact and approximate. Auto is probably the best one to keep your calculator in for a lot of this work, but again, if you know you want an exact answer, exact. If you know you want an approximate answer, go for your approximate answer. And I guess the other thing I just wanted to say, Brian, before you wrap up, is very good to see a lot of feedback coming through tonight. There was a lot of good questions and a lot of good chat. Great to see, and yeah, hopefully we can keep that going for the last 2 sessions. So thank you for those people who sent questions and chat through today.
Yeah, terrific. Thanks, Stephen. And you know, again, great material and well organised for the session. And I agree with you totally that if people are going to attend the thing live rather than watch the recording later on, the benefit is you can ask questions and then hopefully have them answered. I'm coming back to that slider one, mate. What I did here when I got the sliders, I graphed, hit tab to open up the input, and rather than do a function, what I've done is, because when we do the entry line, you can either enter as a function, which is the normal case, or I can enter as a relation. So I graphed the relation x equals 1.
Sorry, Brian, we can't quite see your screen there, mate. I'll just let you know that if you're actually showing your screen.
Thank you. I better do that.
Yeah, sorry about that, Brian. Sorry to cut over the top of you.
Simply, the reason that you weren't seeing it was because I hadn't shared it.
That's better. Thank you. You can see it now, Brian. Thank you for that.
Yep. I'll just hit a Control-Z to go back to undo what I just did. To get the vertical lines here, what I've done is I went into Menu, and in the graph entry line, rather than enter a function, I've entered a relation. So the first relation I've entered is x equals 1. Of course, that's a vertical line, and that's it there. And then I wanted to get the next one up to, well, we know the previous example was x equals 2, but I'm going to change it from x equals 2 to x equals a. Now, at this point, it doesn't know what a is, and so it prompts me and says, well, do you want to create a slider for that? Which is quite convenient, and I'll say yes. And there it is, it's done. Now, here's the box for the slider. Now, when you place, when they first appear, you have the option to place it somewhere. Think where you're going to place it, because once you've dropped it, it's often a very hard thing to pick up again later on. So here it is. So instead of going up to 2, which it is at the moment, and that's the area under the curve, I can increase the slider, and I could also increase, if I then mapped in for the area, I would map in the area. So that's increasing the slider thing there. The other way to do that is when I mapped in the x equals a, there it is, and you can see it's bold, so it's known to the thing. The other way to put the sliders in is through the menu under Actions, and it's down here, Insert Slider. So that's how you can set that up. So variable 1, well, I could call it, you know, A or B or whatever. This is its current value, that's the range of the slider, and so on, just talking about how it's going to be presented. So that's just a quick one to get back to that on the sliders. We've done quite well, Stephen, I believe, addressing lots of things there. So, again, we look forward to hearing from you again next week, and keep those questions coming, and watch your email for the link to the Google Drive that Stephen mentioned, where you can get copies of Stephen's PowerPoint and those TNS files. So good afternoon to all, and see you again next week.
Thank you, everyone. Thank you, Brian.